Okay, Juliana.
Okay, so hello everyone. Welcome to the Latinx Camp seminar part of this conference. My name is Juliana. I'm a co-organizer of the Green Chemistry category. And today I have the pleasure to introduce you to Dr. John Warner. John Warner, he is one of the founders of the field of green chemistry. He wrote the book that provides the definition 12 principles of green chemistry with Dr. Paul Anastas. He has over 350 patents. He has worked with several companies worldwide, and he has received the Perkin Medal in 2014. He was a tenured full professor at the University of Massachusetts, where he started the world's first PhD program in green chemistry. He has over 120 publications, and in 2004, he received the Presidential Award for Excellence in Science Mentoring from the U.S. National Science Foundation, the NSF, and also from President George W. Bush. In 2022, John received the August Wilhelm von Hoff Medal from the German Chemical Society, and he was also named one of 25 visionaries changing the world, one of the most influential people in the chemical industries. He's also a member of the Club of Rome, and he holds academic appointments in several institutions worldwide, one of them being the Technical University of Berlin in Germany, where they have created the John Warner Center for Startups in Green Chemistry. Currently, John is the president and the CEO of the Technology Greenhouse. So John is an amazing person, and it's my pleasure to have him here with us at the Latinx Camp. Thank you, John.
Thank you. That was such a thorough introduction. I think I can just log off now. We're done. But thank you, Juliana, and thank you for giving me an opportunity to speak with you. What I wanted to do today in this talk is to kind of be very personal and talk about where did green chemistry come from a personal perspective, so that people fully understand the history and why, green chemistry is so important to me. So I'm going to try to share my slides, and hopefully I'm going to do that correctly. If someone can verbally tell me, hey, you're doing it right. Am I sharing it right?
Hey, you're doing it right.
Thank you. Hey, I hear that so rarely. All right. So chemistry is a scary subject. Most people in our society, it's like the monster sleeping under the bed that's going to come out and bite us. If we open up a newspaper, turn on a radio, look on the internet, all we hear about is this is bad, this is toxic, this is dangerous, this is scary. It's like, who in their right mind would want to be a chemist today? Because it's all this bad, scary stuff. And I feel, there's some truth to it, right? There are products that are a problem. There are products that have endocrine disruptors. There are products that are contributing to climate change. There are forever chemicals that are in our products. There's carcinogens and things that cause birth defects. But I think we spend so much time talking about regulations and everything else, we kind of forget a more fundamental question. And I think that the most fundamental question is, why would a chemist make a hazardous material? Let's assume nobody wants to make a hazardous material. No one is intentionally saying, oh, I want a red dye. I want it to be in lipstick. I don't want it to fade. And oh, if it was a little toxic, that would be good. Nobody wants this stuff. So why do we do it? And so maybe instead of looking at how we make molecules, we really need to be examining and thinking about how do we make chemists. So I'm not a science history person. I'm not a historian that can talk about the history of science or anything, but I'm a chemist. Maybe there's something there that's worth looking at. So I'm from a city in Massachusetts in the U.S. called Quincy, Massachusetts. My accent, for people who understand accents, I have a very specific access. It's just a little south of Boston. And Quincy is interesting. No one's ever heard of it, but it's a very famous city in the United States. There are only 36 presidents of the United States, and two of them are from Quincy, Massachusetts, John Adams and John Quincy Adams. And in my opinion, the greatest chemist who ever lived, R.B. Woodward, is from the city of Quincy. Okay, he got the Nobel Prize for the synthesis of vitamin B12, and then he passed away. And you can't get the Nobel Prize after you die. Had he lived longer, I think he would have gotten 2, maybe 3 more Nobel Prizes. Really an amazing person. And he's from the city of Quincy. But I didn't grow up wanting to be a chemist. I'm not somebody that if you saw me when I was a child, you wouldn't say, oh, this person's going to be a chemist. I came from a very, very large Sicilian German family. So I had 42 first cousins growing up within a small radius of my home. And we were carpenters, plumbers, electricians, and things like that. I didn't, we weren't talking about education or anything like that. In fact, when I took mathematics on the second floor of my high school, I thought that was higher education. I didn't know what education was, but my friends were all going to college. And so I decided, well, maybe I'll go to college. And my family didn't understand the value of university. My family didn't understand the value of college. And so they were not that they weren't supportive, but they just didn't understand. And so I worked full time as a construction worker, paying my own tuition. And I went to the University of Massachusetts, Boston, 1980. And it's important because this university really catered to the non-traditional chemist. I don't think student. I don't think I would have gone to school had this not existed. But you see, I didn't go to school for science. I actually went to school for music. I was a musician. And I played in a band called The Elements. Interesting enough, nothing to do with carbon, hydrogen, nitrogen. We kind of sounded like the band The Cars, if you know the band The Cars, but I think with better lyrics. And so we were doing pretty well. We were playing 3 nights a week at different gigs. We actually had a recording contract. We were recording in a studio in Boston when sadly the drummer of the band, my good friend James, he ended up getting cancer, a form of leukemia. And over the course of 6 months, he died. And all of a sudden, my life was upside down because, I was a musician. I was playing in a band. I was doing all these things. What am I going to do? Well, at the University of Massachusetts, even though I was a music major, they believe in a well-rounded education. So I had to take a math course. I had to take a foreign language. I had to take a science class. So as a musician, I still had to take a science class. And so I kind of liked physics, subatomic particles and astronomy. And I kind of like biology, genetics, mitosis, meiosis. So I couldn't pick, should I do physics? Should I take biology? Should I take physics? And so in a moment of inspiration, I said, well, chemistry is kind of halfway between physics and biology. So I'll take chemistry, not because I particularly liked it, but because I couldn't pick between physics and biology. So here I am in the teaching lab at UMass, and one day this professor comes in, Professor Jean-Pierre Anselme. He looks at me. I'm a music major. He's not interested. And he goes to the student standing next to me, and he asks the student standing next to me if he'd like to do research. I overheard the conversation. I'm just lost my friend. I'm trying to figure out what am I going to do. And so I asked if I could follow them into the research lab. And I went into the research lab, and almost immediately, everything changed. All my life, I thought there were 2 types of people. There were artists and there were scientists. And because I was an okay musician, I must be an artist. But when I got into the chemistry research lab, and I realized that chemists created things, imagined things, designed things. All of a sudden I said, wait a minute, I've got this wrong. I bet you the brain activity to compose a piece of music on a piano or the brain activity to design a molecule is probably the same thing. that creating something new isn't science, isn't art. It's something more human. And so once I understood that, I fell in love with chemistry and started to spend 60, 70 hours a week working in the chemistry lab. So by the time I was 19, I published 5 papers in journals and realized I was pretty good about this chemistry thing. Well, because I lost my friend to cancer, I decide I want to work in cancer. And so I go to Princeton University to get my PhD as a cancer researcher. And so I published 12 papers on the design and synthesis of a class of compounds that were anti-cancer drugs. And they actually ended up being this drug called Alimta, sold by the Eli Lilly company. Just to show you the relationship between science and society, I lost my mom in 2002 to cancer. She was receiving the drug that I had helped design 15 years earlier. So the relationship between science and society is crazy. And if you go to the Princeton campus, this amazing chemistry building is now built entirely on this one molecule. Now, I played a tiny role. It's not a big role. There's hundreds of people working on this project, but I am the research signature witness on the patent for this thing. And so before I graduated from the university, I had 2 universities offering me tenure track positions that I didn't even apply for. So I assumed I was going to be in academia and I was going to be a professor of medicinal chemistry. When strangely, this man from Polaroid, the instant photography company, came to visit the campus at Princeton. He brought me out to lunch and he offered me a job to work in an exploratory research group at Polaroid. Now, I said to him, "Sir, I'm a medicinal chemist. I'm going into academia." He told me how much he was going to pay me. I said, "When do I start?" And all of a sudden, I'm an industrial chemist working at Polaroid, one of the coolest companies around. Edwin Land was the founder of Polaroid. At this point, only Thomas Edison had more patents than Edwin Land. So great of an inventor that Edwin Land, he got the Perkin Medal in 1974. How cool is that? Then they gave it to me. So seriously, how cool can it be? And I realized that I was pretty good at this invention stuff. The next thing you know, I'm over 40 patents in holography, medical diagnostics, all these different things that I start inventing. But you got to ask yourself, what would a medicinal chemist do at a place like Polaroid? As a medicinal chemist, I'm doing everything in bags of water. What is a cell? A cell is a bag of water. It's at room temperature, ambient pressure. And so everything is that. And now I'm in an industry where everything is in stainless steel reactors, high temperature, high pressure. And say to myself, biology, the molecules in nature are so complicated, we can't even synthesize a lot of them. But not only that, everything in nature is done at room temperature and ambient pressure. Why is it that we can't do that as humans in normal chemistry? And so I could give an entire hour-long lecture. The end of this is I came up with this science called non-covalent derivatization. And essentially, it's what I realized is that in biological systems, many, many things happen because of how molecules interact with each other, how they phase separate, how they hydrogen bond, how they do different things. And so many people change molecules by making covalent derivatives, methyl, ethyl, propyl. But I said, could I make derivatives non-covalently? And so essentially, could I change the solubility? Could I change the physical properties like nature would by changing these non-covalent interactions? And so came up with the science. And I'm such a nerd. The license plate of my car is NCD, and for non-covalent derivatization. And at Polaroid, one of my inventions was based on the science. Okay. And so Polaroid wanted to go to large scale manufacturing. In the United States, you can't just go manufacture something. You have to have approval from the EPA. Okay. It's called TSCA. And it's like low volume exemption, pre-manufacturing notification. But here's the thing. The way the EPA works, when you submit a document to be approved by the EPA, they look at everything they've already approved. And if what you're proposing looks like something they already approved, they go, okay, approved. But if it's new and different, they don't really have a protocol. They don't know what to do. And because non-covalent derivatization is a whole science that I created, they didn't know what to do. And they go, oh, small particles, molecular complexes. So Polaroid put me on an airplane from Cambridge, Mass, and sent me to Washington, D.C. to meet with the EPA. Okay, I'm a little scared, I'm a little bit nervous, but I'm also a little mad. And I go to the Office of Pollution Prevention and Toxics at the EPA, and I meet the branch chief, this guy named Paul Anastas. Wait a minute. Remember the person that I followed into the research lab when I was a music major, that the guy asked if he wanted to do research? It was him. I've known him since I was 11 years old. We went to UMass Boston. And in fact, I was playing in a funk band with his older brother. We kind of sounded like Tower of Power, but was not as good at lyrics. And so there's him, there's me, there's my older brother. And this guy playing the guitar. If you've ever been to Las Vegas and you look at all the billboards in Las Vegas, the guy who plays Rod Stewart in Legends of Rock, that's him. Has nothing to do with this talk. I just thought it was kind of cool. So anyways, I can say to Paul, wait a minute. We've been synthesizing this with all these solvents, all this energy and hazardous reagents. Now I've invented a new technology that's aqueous, non-toxic, but you're giving me a hard time, not because of toxicity or environment. You're just giving me a hard time because it's different. Isn't anything better for human health than the environment always going to be new and different? And if the EPA makes it difficult to do new and different, isn't that a problem? All right, so I'm having these philosophical discussions, Washington, D.C., and this big government agency, and things that keep going on in my life. At this point, things are going really well. I've gotten promotion after promotion after promotion. I've got now a bunch of patents, a bunch of papers. In fact, Celebrity Magazine does a story with me on the cover, and my head is this big. I am the greatest chemist who ever lived. When disaster happened in the worst way imaginable. Here I am, very, very successful, and I lose my 2-year-old son to a birth defect. My son John was born with a disease called biliary atresia, where his liver was detached from his intestines and he couldn't metabolize water and soluble nutrients. He got surgery at birth, and at 2 years old, we lost him. He passed away. Lying in bed the night of my son's funeral and staring at the ceiling, and I'm asking myself, I wonder if something I touched in the lab caused my son's birth defect. I wonder if, heaven forbid, something I got an award for or a prize for caused his disease. I didn't feel like some amazing scientist. I felt something was missing. There was a missing element to what I called chemistry. All right. The answer to the question, did something I work with cause this to my son, didn't bother me as much as the fact that I couldn't answer the question. I felt this is something I should know, shouldn't I? So there's books around this time. This is about 1991 time frame. Books are coming out like Our Stolen Future and things like that's talking about the impact of chemistry and stuff. And I realized that I'm probably one of the most successful chemists on the planet. Right? I've already synthesized over 2,500 molecules with my own hands, not repeat syntheses, new molecules. And I realized never had a course in toxicology, never had a course in environmental mechanisms. How could I be such a successful chemist and literally have no idea what makes a molecule toxic? If I work with a known molecule, I can go get a document, the LVN, these different government documents. But what if I make a new molecule? How do I know if it's toxic or not? Shouldn't that be part of my education? How do I know if it's going to biodegrade or not? How do I know if it's going to contribute to global climate change? Every year, just in the United States, now the world is a big place, there's a lot of other, but just in the United States, we graduate 15,000 undergraduates every year. in chemistry. 3,000 masters, 3,000 doctoral degrees. In 2004, more women started to become chemists than men. What could be more important to the field of chemistry than some understanding of what causes molecules to hurt people or the environment? And yet, to get a degree, there are back then, 0 universities required anyone in chemistry and material science to learn anything about toxicity and environmental impact. So, although this is terrible, now all of a sudden it's not surprising that we have all of these problems. This isn't an epic battle of good and evil between industry and environmentalism. This is something missing from the chemistry curriculum. Okay. But there's hope, because that means, what if we add this knowledge to the chemistry curriculum? So Paul Anastas and I, the guy at the EPA and me from Polaroid, we realized that the world didn't need a philosophy. The world didn't need a social movement. It needed a mechanistic science. In the same way that we have this thing called analytical chemistry, organic chemistry, physical chemistry, we needed a mechanistic science so that we could have journals and textbooks and classes and conferences and workshops. And that's the birth of green chemistry. So Paul Anastas and I, we wrote this book called Green Chemistry, and what we wanted to do would be very precise. In sustainability, there's a lot of confusion. So we didn't want to contribute to confusion. So people go, what is green chemistry? Well, there's an entire chapter. What is green chemistry? Well, what's the definition? Well, the definition is clearly in the green chemistry: the utilization of a set of principles that reduce or eliminate the use or generation of hazardous substances in the design, manufacture, and application of chemical products. And if that's not enough, we expand it to 12 principles that are mechanistic science. And I got to tell you, his book has been translated to over, I think 12 languages at last time. There's going to be a Portuguese translation coming out very, very soon. I have been to over 90 countries, meeting kings and queens and presidents and prime ministers. And I'm just a name on a book. There are thousands of people in the world doing green chemistry now that are doing amazing things. I'm just a convenient figurehead, but it's amazing to see how many people have just decided to passionately make this happen. And so to me, green chemistry, yes, green chemistry has to have some sustainability attribute. It's safer, it's less toxic, it's better for the environment, but that's not enough. It has to be used. And so it has to have better performance, because if it's not as good as the stuff that's out there, people sadly won't use it. And it has to have the right cost. We can't have just rich people being able to be safe and sustainable. So that by definition, a technology that works better, costs better, and oh, by the way, is better for human health and the environment, then you have green chemistry. Okay. And that's why the nonprofit Beyond Benign is called Beyond Benign, because it's not enough just to be benign. It has to have better performance and better cost. But you can't do it just because you want to. You need to have the skills. And so I left Polaroid and I went to the University of Massachusetts. I became full tenured professor of chemistry and chair of the chemistry department, and full tenured professor of plastics engineering in the Lowell campus. And we started the world's first PhD program in green chemistry. Everything in a normal chemistry program, but we added a 1-semester class in mechanistic toxicology, a 1-semester class in environmental mechanisms, 1-semester class in law and policy, and other things in design and everything. A very successful program that had hundreds of students come through it. So essentially, it's not the birth of ethics. It's not that people before green chemistry don't care. But what's interesting is historically, when we had tried to make things safe, when we try to do things, when we talk, we say, oh, well, chemistry has to be toxic. But it's okay because we wear gloves to protect our skin. We wear masks to protect our lungs. We wear goggles to protect our eyes. We install filters and smokestacks to protect the air, the land, and the sea. Problem with this is that, yes, this sometimes works, but it also sometimes fails. When I showed that first slide with all those headlines, those, if you ask the people, say, oh, everything's fine. We've got the glasses, we've got the goggles, but accidents happen. People are people. And so green chemistry says, well, there's the exposure. We can just protect people by limiting how they're exposed. But the revolution that is green chemistry is saying, instead of focusing on exposure, let's look at the molecule itself and reduce the hazard. I can look at a molecule and make the color red. I can make it stick to a fabric. I can make it not oxidize in the sunlight. I can also make it non-toxic if I understand how. I can make it biodegradable, but it's not enough to want to. I need to have the lessons in school to teach me these mechanisms. So now there are so many mechanisms in sustainability, responsible care, safe and sustainable resilience, all these different approaches. And what makes me sad is that we're in this world where everything's a competition. Someone says, this is the new approach, and this is the old approach, and this one is better, and this one's not. And that's probably why we're in the problems we have today from sustainability. We don't have to have these competitions. Every single one of these approaches are great. There are people who with very vulnerable have gone and proposed these things. If someone wakes up in the morning and says, I love this approach, instead of saying, you're wrong, you should do this, very egotistical thing to do, we need to embrace one another and help each other do what it is that they're passionate about doing. Okay, but to do that, we have to see things in a clear way. And so the way that I look at it, we take natural resources and we extract molecules and ingredients. Then we synthesize materials and components, and then we manufacture products. And if we do this very well, the products stay in use and reuse for a very long time. But sometimes we're going to have to turn those products back to materials and components by mechanical recycling. And then sometimes we're going to have to turn the materials and components back to molecules and ingredients through molecular reprocessing, what I call the materials metabolism. And then sometimes we're going to have to let those molecules and ingredients degrade back to natural resources, and hopefully we're going to maintain stable ecosystems. This isn't a circle. It's kind of like a pendulum that if you go clockwise, that is the human-built world. And then inside, when you go counterclockwise, that's returning back to nature. And that overlap on the bottom is actually a mathematical algorithm of sustainability. And so what we need to do is realize that when we do all these things, we've got to keep it not just the things that we want to have happen. We also got to worry about the accidents and the problems. So when we do the manufacturing, there's going to be leakage. And when that leakage happens, there's a loss of sustainability. When we do synthesis and molecular processing, there's going to be leakage and there's going to be a loss of sustainability. When we do extraction and degradation, there's going to be leakage and there's going to be a loss of sustainability. So we need to make sure that we're thinking not only of what things happen that we want to have happen, but also worry about the things that are going to happen that we don't want to have happen. Because when people do maps like this, they never say, oh, every once in a while we'll have an oil spill, or we'll have plastics accumulating on the oceans, or we're going to have a train wreck in Ohio that's going to have toxic emissions or CO2 in the atmosphere. So we have a moral and ethical responsibility to also care about leakage and what's getting out. So that means we need to, the best way to make waste go away is to redefine it as a feedstock. Can't do it just by wanting to do it. People can say circular economy, circular economy. That doesn't happen because we want it to happen. It has to be invented. We need the skills so that we can take these emissions and use them as feedstocks. And then all of a sudden, everything makes a difference. So if we invent technologies that help people change their behavior, or invent technologies that are intrinsically in harmony with nature, we need to do both. Some people say, oh, everything should be circular, everything should be recycled. And other people say, no, everything has to be bio-based and biodegradable. It doesn't need to be one or the other. It should be both. And we should be working together. And so that's the whole point of this, that all of this has to be reinvented. But again, it's not going to be reinvented just because we want it to be. We need the skills. I want to play the violin. Okay. Doesn't matter how much I want to play the violin. It's not going to make me play the violin. I can go to a concert and listen to someone else play the violin. That's not going to help me. People can yell at me and say, you should learn the violin. That's not going to help me. I have to have a mentor, have to have a teacher, and I have to practice, practice, practice. Well, it's the same thing when it comes to sustainability and chemistry. It's not enough to want. We need the skills. Because here's the thing, of all the things in our society today, I think less than 10% are truly sustainable. 90% still need some fixing. Sometimes they're big problems, sometimes they're little. There are some things that are easy, and I think pretty soon we'll have about 25, 30%. But I think right now, 70, 75% of the technologies, they haven't been invented yet. This isn't some epic battle of good and evil between industry and environmentalism. Remember my definition, better performance, better cost. Oh, by the way, better for human health and the environment. Who would reject that? Who wouldn't want to use that? So the assumption is that the biggest barrier to sustainability isn't the desire. It's the ability. We haven't invented them yet. All right. And here's the problem. Every time we go to sustainability conferences or universities have sustainability programs, mostly what they do is they talk about why. Oh, look at climate change, look at plastics in the ocean, look at this. And that's important. Or we talk about what? How are we going to measure it? Should we do LCAs? Should we do, how do we monitor and measure it and characterize it? We need metrics, metrics, metrics. Problem is you need something to measure. Talking about why and talking about what doesn't solve the problem. It describes it, measures it, but doesn't solve it. The most important part, but what's little done, is the how. And if there aren't people doing the how, all the urgency in the world and all the metrics in the world aren't gonna help society. And so essentially with all the molecules and products in the UN SDGs, I think that's a great thing. The 17 UN SDGs, when someone says to me, chemistry only does 4 or 5 of the UN SDGs, those are fighting words to me. I would say that all 17 have critical chemistry components to it. If you don't believe me, let's schedule a time. I'll talk about that. But we need this mechanistic connection, and that's the magic of green chemistry. That is the science molecular level mechanism that connects molecules and products to the sustainability objectives. But here's the thing. If you look at industry over the last 30, 40 years, we're not that good at inventing new products. In 1980, companies came out with new products all the time. In 1990s, it went down a little. In 2000s, it went down a little. In 2010. So our productivity making new products isn't as good as it used to be. Has nothing to do with sustainability. People say, oh, it's hard to commercialize sustainable products. No, it's hard to commercialize new products. We're not doing very good. What happened is 30 years ago, we would do invention is bumpy. You work, you invent, eureka, so it's bumpy. You can't really make a linear line to it. And then once you do all the research, then you can do development. And development is kind of planned. So on the x-axis, we have time and resources. On the y-axis, we have the knowledge development. And you've got 3 levels of research and 3 levels of development. And this is how it all works. But the thing is 30 years ago, academia did this and industry did this, and there was an easy handoff. But now in 2024, because everybody's worried about the impact factor of the journal and all these metrics, we want to get, when I was, someone publishing 4 papers a year was amazing. Now we have professors publishing 200 papers a year. Oh my God. And what's that's done is it's gotten us doing very little pragmatic work. And at the same time, money and budgets have had industry do less research. So now what used to be a nice continuum, there's this big hole, there's this big gap. And the most important thing from my perspective is the filling of this is what's called entrepreneurship. Now, I'm not saying everybody should become an entrepreneur. What I'm saying is people in academia need to understand entrepreneurship. People in industry need to understand entrepreneurship so that we can make this work. Okay. And here's the thing. While there are infinite molecules and materials and there are infinite products, it's like the land of Mordor trying to make it across. People have been struggling. How do we go from molecules to products and back? But I'm going to let you in on my secret. My secret is having been doing this for almost 40 years, what I've realized is although there are infinite molecules and there are infinite products, there's actually not that many molecular mechanisms. The nouns, the products and the things is infinite, but looking at the molecular level to that transformation, maybe 65, maybe 70. And if we focus on these mechanisms, what chemists should be doing, all of a sudden the world changes. So that essentially a product is really defined by materials properties like color, flexibility, hardness. That's still not a molecule. The material's property is defined from a material mechanism. Polymer, crystallinity, Hansen parameters, still not a molecule. The material mechanism is defined by molecular mechanisms. Bond rotation, molecular topography, things like that. Now I can look at a molecule, say, what molecular mechanisms can this make? I can look at the molecular mechanism, say, what material mechanism does this do? Then I can look at the material mechanism, say, what material property, and I can invent a new product. Or I can look at a product and say, how can I make this product better? Well, I need this material property, I need this. So you go in either direction, and that's how we invent new materials. And here's the key. When you list the materials properties that you want, if you list things like toxicity, GHG, potential biodegradation, now you're doing green chemistry. And you can't do that if you don't know what the materials mechanisms and the molecular mechanisms are. But if you learn those mechanisms, then all of a sudden this is no different than color, flexibility, or anything else. All right. And so we can use intuition or we can use, computational tools to help us go between each of these. You can't go from molecule to product, but you can go molecular mechanism to material property. So I could use this to invent a new Apple product. Right. And that's okay. That's pretty good. But you know what? I can also say, wait a minute, chemistry's been around for 200 years. Biology has been around for 3.8 billion years. What a long R&D cycle. And so instead of just looking at an Apple product, why not look at an apple and ask, how does that apple work? How does the oxygen barrier, how does the water barrier, the viscosity, the cell structure, if I, with humility, learn from nature and figure out these mechanisms, then I can come back and start making new products that are inspired by nature, that are biomimicry or whatever you want to call it, to essentially start solving some of these problems. All right. And so there's what the product does, and then what the technology is. And this is really important to keep our mind on that. Solar energy is important for sustainability. But if we're using toxic materials to make a solar panel, well, we're just giving someone else a problem tomorrow. And so when we do green chemistry, when we do sustainability, we can't just look at what the technology does. We have to worry about also what the technology is. And that's why this mechanistic approach is useful. So my wife and I, Amy Cannon, if you haven't met her, I urge you to do so. We, in 2007, we realized that we wanted to focus on this. And so we left academia and we have this shared vision. We envision a world where the chemical building blocks of products used every day are healthy and safe for humans and the environment. Amy runs Beyond Benign with Juliana. The mission is fostering a green chemistry community that empowers educators. And then I do the invention to show the world that it can be done. All right. And here's the thing, using green chemistry and using these mechanisms, me and a very small team of people Here's a group. Here, the Technology Greenhouse. We're up in the Boston area. We have labs around here: material science lab, synthesis lab, AI lab, and then the headquarters in Andover. We have been able to, in just like 15 years, 12, 15 years, we've filed over 360 patents. All right, we've invented technology. These companies on the bottom here, they have publicly issued press releases. Oh, we worked with John Wanna, we invented this. There are 4 times more companies that haven't gone public, and I'd never talk about a company if not. And the companies on the top are the companies that I have spun out that people have created based on inventions that we have done. And so it's important to realize that green chemistry, yes, there's a moral and ethical part to this, but it also makes you a better chemist, makes you invent faster and more cost effective and have it. So I want to finish with some examples. What does green chemistry look like in the real world? Okay, my first example, this molecule here is called copper ATSM. It is very insoluble, but if you put it in DMSO with a bunch of surfactants, it actually has interesting neurological behavior with laboratory animals, but you could never give humans surfactants and DMSO. So using the green chemistry science of non-covalent derivatization, we're able to make it orally bioavailable and make it cross the blood-brain barrier, and we synthesized, manufactured it at scale using mechanochemistry. We started a company called Collaborative Medicinal Development, went through phase 1, phase 2, phase 3 clinical trials. Right now, it's looking really promising to be a potential cure or at least a drug to help ALS. Lou Gehrig's disease. The long way to go. It's not a done deal yet. Still got a lot to do, but this is super promising. I would argue there's no way I could have done this if I didn't use the principles of green chemistry in my materials mechanism, metabolism route. Another example, when an insect gets bigger, it sheds its exoskeleton and very quickly turns hard and black. I'm looking at that and I'm saying, oh, there's a process in nature that goes from white to black. People color their hair and they use really nasty toxic materials when they color their hair. It ends up being a tyrosinase oxidative cascade. So what I did was I designed a set of catalysts, an iron catalyst, a manganese catalyst, and controlled the kinetics and the thermodynamics. I didn't want to grind up dead bugs. I thought that was nasty. So I found these beans, velvet beans, and I bought a bunch of gray hair and I put it in. And oh my goodness, it worked. It was non-toxic. It was permanent, didn't wash out, didn't fade. But it was interesting because it was all over the place. And what I realized is I wasn't dyeing the hair. I wasn't painting the hair. I was restoring the human pigment. Look at me. If I put it in my hair, it goes back to exactly the color my hair was before I went gray. My friend with black hair, it goes black. My friend with brown hair goes brown. The same bottle, the same chemistry, put it in our hair, it restores the human pigment. And just like your own normal human pigment doesn't fade, doesn't wash out. So I realized in the same way that everyone has a fingerprint, everyone has a hairprint. And so we started a company about 10 years ago called Hairprint, and it's a direct-to-consumer material. If you act right now, myhairprint.com for $29.99, they'll throw in a set of knives. This is a product that's been on the market for 10 years, that's non-toxic, environmentally benign, and I promise you, if I didn't use the 12 principles of green chemistry in my materials metabolism scenario, I don't think this could have been invented. All right. Another example, asphalt pavement. There is billion miles of asphalt roads in the world. The sun and the air oxidize the surface, making it brittle and hard. So every year, 10% of all roads are repaved. But because it's brittle and hard, you maybe use 5–10%, but most of it goes into a landfill and we buy new petroleum and new aggregate to make it. I'm a hockey player and I dream of the street Zamboni, have a truck come down, dig up the old asphalt, put a catalyst in to reverse the oxidative damage and pave it. And so I came up with this catalytic system and created a company called Collaborative Aggregates. There's two products. One is a catalyst that goes into the asphalt when you repave the asphalt, and another is in an aqueous emulsion to preserve the asphalt. This company is selling tanker trucks of stuff all around the United States. Took from an idea in my head to starting this company took like 18 months. Okay, could not have done it without using the principles of green chemistry and the materials metabolism. This example, you see this picture, it's like an optical illusion, birds and fish, and when do they turn into each other? In biology, there are a lot of transitions that are gradual. If you look like electron transfer across a mitochondrial matrix, it's not one big jump, it's a bunch of reversible jumps. So I said, well, if I can synthesize a semiconductor that's a hybrid inorganic organic thing that self-assembles and slowly turns into a chromophore, and then the chromophore self-assembles and slowly turns into an electrolyte, it has this gradual thing. Turns out it is the highest dye-sensitized solar cell in history. It works so well that in a very dark place, it's still making electrons. So we started a company called Ambient Photonics, and the company Amazon has invested nearly $100 million, and we're in manufacturing in California for this stuff. And what it is it's for indoor electronics, anything that's powered by a battery using low light. It doesn't power the device, it constantly charges the device. Okay, and again, could no way have done this without using the principles of green chemistry and the materials metabolism. This interesting example, you know the sunglasses, you go outside, they turn dark, and you go inside and they turn clear. Played around methyl ethyl propyl butyl made essentially instead of color, it goes from hydrophilic to hydrophobic. If you make a super hydrophilic polymer, it'll absorb water. But if you want to get that water out, it's too strong. It takes a lot of energy. But what I did is put this passive thing so that I can turn something hydrophilic to hydrophobic and back. So imagine that I have an umbrella. And when the sun is up, water absorbs on the underside of the umbrella. When the sun goes down, it rains pure water, so I can desalinate and purify. Have this happen in the shadow of a windmill in a millisecond time frame will be powered by LEDs. So started a company called Mistminer to do this. Again, the 12 principles of green chemistry and materials metabolism was necessary to do it. Next company is Noir Materials. Started this just the beginning of this year. And this one here, if you have a biodegradable polymer, it's usually not very strong, doesn't have good properties. If you cross-link it, if you make it a better material, it's no longer biodegradable. So it's one or the other. But using the same chemistry that I used for the hair color, I can make the polymers now ballistic, like bulletproof strong and super, super stretchy, but still biodegradable. And so this is an example. And in my last example, I wanted to call this Firefly, but there's too many companies called Firefly. So Italian, I'm wondering what Spanish and Portuguese, but in Italian, Luciola is Italian for Firefly. Okay, and so I called this company that just started last month, my newest company. What I do is I take wireless LEDs. There are no wires to them. You need an inductive coil. You know how like you can do wireless charging of your phone? I make these LEDs that are wireless, and I coat them with chemistry, and I make photocatalysts that have an on and off state. Then I fill a flow reactor filled with it, and I put an induction coil around it, and depending on the electronics, the frequency, I can turn on and off selectively different LEDs that are doing photochemistry, so I can either do synthesis, I can do remediation, pulling something like PFAS out, or I can do bioseparations by new ways of doing chromatography by changing the polarity of the solid support and doing that. And so this is the latest company that's excited that is all built on the green chemistry principles. So these are just examples, and what I'm trying to say is that I don't think me and my team, I've worked with only like 20 people over the last 12 years doing all of this work. I think that, yes, green chemistry morally and ethically is important, but it also makes you faster and more creative as a chemist too. Okay. But what worries me is that we still have so long to go. There's so many more things. We need more people to be learning how to do this and getting invention. And again, it's not going to happen just because people want to. We have to change the way people are taught chemistry. And so my personal hero is my wife, Dr. Amy Cannon. And you can see Juliana is working with Beyond Benign. These people are doing the most important work in the world because they're not just talking about what we should do or why we should do it, but they're talking about how. And the way we do it is by teaching it, getting it into the universities. And so one of their programs is called the Green Chemistry Commitment. And they have had now almost 200 universities globally have signed the Green Chemistry Commitment. There's 114 currently US signers. All right. And every day now someone else is signing. And there's now 79, and again, every day more from Canada, Europe, Latin America, and global universities signing the Green Chemistry Commitment. And in my opinion, this is the most important thing. That the world thinks that this is an epic battle of good and evil, and it's just wanting companies to want to do it. But if a company wants to do sustainability, but the people working for them don't know how, all they can do is hire lawyers to fight regulations. But if we can slowly change the field of chemistry, I believe in people. I think that if the next generation of chemists working in industry, working in academia, they understand green chemistry and learn the skills of green chemistry, look out, world, we're going to solve a lot of problems. But it doesn't happen because we want to. It has to be taught. And so if my request to people listening to this talk is if you belong to a university and you've signed this commitment, thank you very much. If you and the universities you're associated with haven't signed this commitment, please go to this website, talk to Juliana. Let's get this signed because there is no sustainable future without chemists inventing it, and chemists can't invent it if they don't have the skills. So thank you for sharing some of your session here today with me and giving me an opportunity to share with you my thoughts about green chemistry. I hope you find this useful. Thank you so much.
Yay. That was very, very, very useful as always. So thank you so much, John, for your third presentation of the day. We really appreciate you being here with all of the strength you have left.
Mhm.
So John has a couple of minutes left because he needs to run to another thing. So we have a question from Cynthia in the chat, which I think is very interesting. So Cynthia is saying that many industries, they see quality assurance certifications like the ISO 9000 to highlight their commitment to quality. Sorry about my dog. We have seen certifications from organizations like LEAF and like Green Lab. So she's asking if you think we might see a green chemistry certification for larger chemical companies in the near future to encourage better practices in green chemistry, or if you think there is a viable or important direction of this. So
Very important question, couple different things. We have ways of measuring things that have been invented, and we can spend time measuring that. But again, my problem is that 90% of things haven't been invented yet. So we don't have things to measure. And interestingly enough, this is kind of philosophical, but if I want to run the marathon and someone says, how fast do you want to run? That's almost not relevant, right? I want to run as fast as I can run. Knowing that speed isn't going to change anything in how I exercise and how I practice, because I just want to. It's the same thing with green chemistry. We want to make the safest, the most non-toxic, the best technologies. So when it's after it's invented, we need these metrics, and they are important for our society. But in a strange way, they're not that important to invent the technologies. They're important to describe them after the fact. And here's the thing that's most shocking, in my opinion, industry is far ahead of academia when it comes to green chemistry. Every company has people working in green chemistry because they're trying to do it. I'm actually surprised at how slow academia has been to change. Industry changed much faster than academia. And unfortunately, industry can change. A company can say, we want to do green chemistry, but if their chemists don't know how, what good is that wanting? And so until academia catches up, 200 universities is amazing. Okay. The amount of work Beyond Benign has done is amazing. But remember, there's almost 10,000 universities in the world that have chemistry programs. So 200 is not a big percentage. We got a long way to go. And so for me, I do think the My Green Lab and these things, those are the custodial evaluation of what you already do. Doesn't look forward to what you need to do in the future, which is not more important, not less important. It's just different. And so green chemistry focuses on inventing the future. These metrics usually are how we evaluate the present today. Both are important, but they're different.
Thank you, John. I see a question from Liza, but John needs to run, Liza. So I'll ask you to. I'm gonna send this question. I'm gonna send this question to John. If that's okay, John, because I don't want to. Yes. So I don't know if Francisca has anything else to say.
Actually, I just want to thank you, John, for your time. We know that you have a very busy schedule, and
My pleasure.
We thank you for taking the time.
Thank you. Thank you, everybody. Thank you, because the world needs you doing what you're doing. The people who have taken the time to listen to this talk, I try not to cry at that. You're changing the world. What you're doing is amazing, and the world needs you. So thank you. Why wouldn't I take whatever time it takes to come and talk to you? So important what you're doing, and just thank you.
You're welcome, and we hope you have a nice talk for the fourth one, actually. So yeah, take a few minutes, and thank you for having a time with us. Thank you for all of you to come to our third and last talk of this wonderful week of the Latinx Chem Twitter X conference. And this talk is gonna be uploaded in our YouTube channel, so you will see it soon there. And if you have any more questions, you can leave it in the comments, and we'll make sure to give them to Juliana and also John if we have the time to, so they can answer you further. Yeah. So thank you, everyone.
Thank you.
And have a very nice weekend. Thank you for everything.